Hello everyone, today we are going to present a new paper that addresses the challenging task of monocular depth estimation. Our approach, titled Hypergraph-based multi-scale representation fusion for monocular depth estimation, introduces an efficient framework for overcoming the inherent ill-posed problem in the MDE task. The authors are from Tsinghua University. First, the introduction. Monocular depth estimation is a classical task in computer vision. However, the problem is inherently ill-posed and ambiguous. Existing transformer-based methods mitigate the substantial computational overhead by employing local attention mechanisms, which lead to depth estimation errors caused by overfitting the image's local textures, as the figure shows. Furthermore, transformer-based methods still struggle to effectively utilize multi-scale visual features, despite the critical importance of multi-scale information in MDE. To address these challenges, we introduce a semantic consistency enhancement module, which effectively improves the representation of multi-scale features by leveraging hypergraph convolution in the semantic space. We further propose a geometric consistency constraint module, which provides geometric guidance to reduce overfitting to local features, as the figure shows. The contribution of our work can be summarized as follows. Firstly, we propose a hypergraph-based multi-scale representation fusion framework that effectively aggregates cross-position patch features and attention weights generated by a transformer-based backbone while maintaining an acceptable computational cost through a semantic consistency enhancement module. Secondly, we introduce a geometric consistency constraint module that learns the correlations between patches and their surrounding context to reduce overfitting errors caused by excessive reliance on local features. Additionally, we introduce a GCC loss, based on cross-entropy loss, to supervise the training process. Furthermore, we design a correlation-based CRFs module to filter relevant patches for attention computation without being constrained by fixed window sizes utilized in previous works. Lastly, extensive experiments on 4 widely used datasets demonstrate that our method significantly outperforms state-of-the-art approaches while exhibiting superior generalizability in zero-shot testing. The pipeline of our hyperdepth. We propose a hypergraph-based SCE module to aggregate the multi-scale and cross-position information from different patches of the whole image. Moreover, we design a clustering-free hypergraph construction block to generate the approximate hypergraph incidence matrix. Lastly, we construct the correlation-based CRFs module based on a regression layer to generate the final depth map. To comprehensively fuse that multi-scale and cross-position information from the encoder, we propose the hypergraph-based semantic consistency enhancement module to improve the patch representation in semantic space. Specifically, our proposed module can be summarized as 2 stages: cluster-free hypergraph construction and hypergraph convolution for semantic consistency enhancement. Moreover, we introduce a GCC module to supervise the cross-position patch correlation hypergraph learning process. Intuitively, similar patches across the entire image belonging to the same object or plane tend to have similar depths. The geometric information provided by GT depth is crucial for the MDE task. Therefore, we generate a GT consistency score for each patch relative to its K equals 8 surrounding patches based on GT depth. Lastly, we propose a correlation-based CRF method that computes the query vector Q and key vector K for related patches across the entire image using the hypergraph incidence matrix H. Then, we add relative position embedding P and generate a potential function for CRF. For an end-to-end training process, we propose a combined loss function consisting of a scaled scale invariant loss and a geometric consistency constraint loss. Here are the experiment results. To evaluate the performance of our proposed hyperdepth framework, we have conducted experiments on Kitty and NYU depth v2 datasets compared with recent methods such as diffusion depth, DC depth, and eco depth. The experiment results are demonstrated in the table. We can observe from the table that our methods achieve better performance in outdoor scenarios. Besides, our method surpasses other previous leading approaches with different depth constrictions on both indoor and outdoor scenarios. For visual comparison, we provide a qualitative comparison of the Kitty official online benchmark for outdoor scenes. The results obtained from the official online server indicate that our method offers significant advantages over DC depth, particularly at greater distances. That's all we have for today. Thank you all for your attention. If you have any questions, you can contact us via email.